So in this video, we are going to explore certain properties of the partial molar property. We are going to relate that to properties such as internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. And the information on the board is coming from the previous lecture, where we have started from the assumption that the volumes may not be additive upon mixing, or energies may not be additive upon mixing due to the interactions between the molecules. So here is the definition of our partial molar property. Theta is the general thermodynamic variable. We are going to just give names to the partial molar property and proceed from there on. Now let's start from the energies, the extensive energies: internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. Remember that enthalpy was U plus PV, Helmholtz free energy was U minus Ts, and Gibbs free energy was U plus PV minus Ts. And in this group, I have written the extensive version of the properties. The intensive version of the properties follows similarly. H is equal to U plus PV, A is equal to U minus Ts, and G is equal to U plus PV minus Ts. Extensive, intensive. Now I'm going to write the partial molar counterparts of those relationships. H is equal to U plus PV, A is equal to U minus Ts, and G is equal to U plus PV minus Ts. You see the thermodynamic relationships maintained their structure even when we were using the partial molar properties, or partial molar properties also follow the thermodynamic relationships. Nothing fancy about it. Now, given this, let us do a little bit of exploration of the domains where we have the Gibbs free energies. The domain of Gibbs free energy was T, P, and now we have constituent materials. Gibbs free energy was a function of temperature, pressure, and now we are adding the constituents because now we are dealing with mixtures. Now, starting from this, let's write the total derivative of the Gibbs free energy. This is going to be equal to del G over del T at constant P and Ni, all of them. I can write as N total, all right, times dt, plus del G over del P. And this time I keep temperature and number of moles constant times dP, plus summation of all the components del G over del Ni times dNi, where I keep temperature, pressure, and Nj different from I constant. So del G over del T at constant P and Ni is equal to minus S. Del G over del P at constant T and N is V. So this expression becomes minus S dt plus V dP plus sigma over all components del G over del Ni, temperature, pressure, N, J different from I, dNi. And this term is called the chemical potential. Sometimes we refer to that as Ni. This is partial molar Gibbs free energy. Gibbs free energy. Partial molar Gibbs free energy. Del G, partial derivative of the Gibbs free energy, total Gibbs free energy with respect to component I, where I keep temperature, pressure, and all the other components constant. So this is for the Gibbs free energy, mu I or Gi. All right? Now let us derive something similar for H. All right? For H. Now H is equal to, H is a function of S and P. And now we have Ni in our equation. Now we have mixtures. Now let's derive the expression for the H. Similarly, del H over del S at constant P and N ds del H over del P S and N dP summation over all components del H over del Ni P S and Nj different from I times D N I. This is not partial molar property. For to be equal to partial molar property, we have to have this equal to temperature, pressure, and J different from I as our parameters. But we are going to, in a moment, show that this is equal to the chemical potential, partial molar Gibbs free energy. Yes, now this is H, this is T ds plus VdP plus this term. All right? Now I'm going to take my stride from Gibbs free energy being equal to Gibbs free energy being equal to enthalpy. All right? So if Gibbs free energy is enthalpy minus Ts, let me do a derivation. dG is equal to dH minus TdS minus S dt. All right? dG is equal to dH minus TdS minus S dt. I'm going to write this dg on this side, dh on that side. Let's see what we're going to get. dg is equal to, I'm bringing this here, minus sdt plus vdp plus, for all components, del G over del Ni, temperature, pressure, Nj different from I, kept constant, times dni. This is my dg. Okay. My dh is equal to Tds plus Vdp plus summation of del H over del Ni. My parameters are pressure, entropy, Nj different from I, dni. Then those two terms. Minus Tds minus sdt. Right? Tds cancels with minus Tds. This Vdp cancels with this Vdp. This sdt cancels with this sdt. And I have this equals to that. All right? So, del H over del Ni, Ps Nj different from I is equal to del G over del Ni, Tp, that is Nj different from I. This is an important conclusion. I'm going to write it over here. Del G over del Ni at constant T, P, N, J different from I is equal to del H over del Ni at constant S and P and Nj different from I. Right? It is your assignment to show that they're also equal to del U over del Ni S and V and Nj different from I, and also del A over del Ni as T and V and Nj different from I are constant. So it's your responsibility to show that. Now let's set our temperatures and pressures constant. Temperature, pressure are constants. All right? Then our Gibbs free energy becomes only a function of partial molar Gibbs free energy, Gi, dni, and that Gi is the partial derivative of the total Gibbs free energy with respect to Ni, right? So we are going to generalize again what we have obtained from the Gibbs free energy to any thermodynamic property, d theta, as summation of theta I, d, and I. And theta was equal to n times theta, remember. So this was ni d theta I, ni d theta at n times d theta plus theta times dn. All right, n times d theta and theta times dn. d theta, which is equal to summation of theta I times dni, follows from the original description. All right? Now let's start from the condition where we set our temperature and pressure constant, so that our Gibbs free energy, total Gibbs free energy, differential change in the total Gibbs free energy was equal to the partial molar Gibbs free energy times the differential change in the number of moles of that component. Then we generalize this expression into the general thermodynamic property theta. All right, and then we started from the total property again in integral form, n times theta to be equal to summation of partial molar property multiplied by the number of moles of that component. So this is the total property. If I take the derivative of this total property, I'm going to have a derivative with respect to 1, keeping the other one constant, and the other one keeping this one constant, right? The derivative of this term is equal to ni d theta I dni, all right? So this is from the theta perspective. From the perspective of n theta, total property, given that this property is a function of temperature, pressure, and C components, different components, is going to give me a derivative with respect to temperature, keeping pressure and n constant, derivative with respect to pressure, keeping temperature and n constant, and derivative with respect to components, keeping temperature, pressure, and nj different from I constant. All right? Now, if I compare those two expressions, this is theta I, partial molar property, right? I have exactly the same expression on this side as this one, so these two will cancel. These two will cancel, all right? And I'm going to regroup these expressions so that I have del n theta, or I will write, instead of n theta, I will write extensive theta, del theta over del t, keeping p and n constant times dt, plus del theta over del p, keeping t and n constant. All right. Instead, I took them to the other side of the expression. I will put the sign as minus, plus Ni d theta I is going to be equal to 0. These thetas are of course partial molar properties. So this is the generalized Gibbs-Duhem relationship. And for the specific situation, if temperature and pressure are constant, what we have is the following expression. Ni d theta I is equal to 0. Why this is useful is going to be very clear when we start addressing examples, but just imagine that we are using a binary. We are looking for the relationships for a binary mixture like the ones you have on the board. Knowing one partial molar property is going to allow you to estimate the other one. This is for number of moles. If we divide this by total number of moles, we get the equivalent in terms of mole fractions. Summation of xi d theta I is equal to 0. This is equally valid. If I divide this one by total number of moles, I get a mole fraction equivalent of the same relationship. So this is the specific Gibbs-Duhem relationship for the constant temperature and pressure. This is the general Gibbs-Duhem relationship, and theta represents any thermodynamic property S, U, P, V, H, U, A, G, and T. Yeah? All right. So let's take this Gibbs-Duhem equation and apply it to the Gibbs free energy. Del G over del T, P and N, the minus in front, times dt minus del G over del P Tnn dP plus Ni dGi to be equal to 0. Now Gibbs-Duhem equation applied to the Gibbs free energy. All right, so del G over del T at constant P is equal to minus S with a minus in front. It's going to be SDT. Del G over del P at constant T and N is going to be V with a minus in front, minus VdP, plus Ni dGi. Right? So if I divide both sides by 1 over n, I can do that. I get this expression for molar properties relating to the mole fraction. All right? The mole fraction equivalent of the generalized Gibbs-Duhem equation for the Gibbs free energy. Now this term is going to be useful. We are going to again revert back to the general form of the Gibbs-Duhem equation. We are going to write del theta over del t pnn dt plus del theta over del p tnn dp plus mole fraction based d theta I to be equal to 0. Now here we established that all the thermodynamics rules apply also for the partial molar property, and so the Gibbs-Duhem also should hold, the generalized Gibbs-Duhem should also hold true for d theta. All right? What is it? This is del theta over del t at constant pnn times dt plus del theta I over del p tnn times dp plus del theta I over del xj dxj t p xj different from I is equal to 0. Okay, so this d theta I is going to be substituted in here. All right, this d theta I is going to be substituted in here, and let's see what we are going to get. D theta over dt, we have d theta I over del t, summation over all components. All right. And of course, these have minus. These are Gibbs-Duhem. These are minus as multipliers. So we have a minus del theta over del t dt. We have a del theta I over del t dt multiplied by the mole fractions of all of the components. This is going to be equal to del theta over del t dt. This term is going to cancel this one, right? After it is being placed into the summation sign. This term is going to, after being substituted in this part, it's going to cancel with this one, all right? And eventually, we are going to get an expression as follows. Summation of xi, this term is going to come, times the summation of del theta I over del xj t p xi dxj to be equal to 0. So now we are going to expand this for a binary mixture. For a binary mixture, we only have one mole fraction. The other mole fraction is dependent on the first one. For a binary mixture, we have x1 and x2 is equal to 1 minus x1. So notice that for a binary mixture, we only have one component to be changed. We have only x1 changing, x2 changes with respect to x1, and we are just taking the summation to the total number of components minus 1. Therefore, we are doing it for only 1. And as a result, our expression reduces to xi del theta I over del x1 tmp times dx1. So when we expand this, we get x1 del theta 1 over del x1 at tmp plus x2 del theta 1 over del x del theta 2 del x1 tmp to be equal to